Day 135, electrostatics example number 31. Here we have two parallel plates. Once again, this is not a point particle problem, even though we're dealing with one single electron, but that electron will be accelerated in this uniform electric field. So let's say this is the electron over here. If it starts over on the right, it's being repelled. It's kind of like dropping a ball to the ground. Same idea as with gravitational potential energy being transferred into kinetic energy. This little electron has electric potential energy that will be transferred into kinetic energy, and it will pick up speed, it will accelerate to the left, and then hit the left-hand plate with a velocity like a ball dropping to the ground. Alright, so bottom line here is we'll need to know some background information. We'll need to know the mass of the electron. I don't expect you to know these. I'll give you these statistics, this data on test. The mass of an electron is 9.11 times 10 to the negative 31st kilograms. This problem, you don't need to know the mass of the proton, but in the next one, problem number 32, problem 32 is basically just the reverse of 31, and you'll need to know the mass of the proton. I'll write it down, 1.67 times 10 to the negative 27th kilograms. If you don't have these written down, just look them up online or inside the cover of your book for those known facts. We also know that the charge on each of these is the charge of the electron. It's, well, Q, the charge is 1.60 times 10 to the negative 19th coulombs. That's always the charge on any electron or any proton. So that information will come into play here. Bottom line now, though, get your equation sheet handy. What we've given you here in this problem, if you read through it, potential difference, that's delta V. So delta V has been given in this problem. Delta V is 15 volts. So you go to look at your equation sheet here, and you look around a little bit. If I have delta V and I have Q, which I have Q, which is the charge of this electron, 1.60, negative. It doesn't really matter at this point. If you look in the equation sheet, the one equation that has delta V and Q is this equation. Delta V equals delta U, potential energy, over Q. What's going to happen here is there's going to be a loss in potential energy transferred into kinetic energy. So we can figure out what delta U is going to be here when this electron goes from one plate to the other plate, because delta V is 15 volts, potential difference, equals delta U over the 1.60 times 10 to the negative 19th coulombs. So delta U is 2.25 times 10 to the negative 18th joules. This is a pretty much straight up conservation of energy problem. It's going to be a loss of that much potential energy as it picks up kinetic energy, just like a ball falling down from a height with GPE transferring into kinetic energy. The kinetic energy formula, once again, is KE equals 1/2 mv squared. So essentially, I'm just going to plug in the 2.25 times 10 to the negative 18th joules equals, and I'll let you finish the problem. Just fill in the blanks here. You know M is up here. So it equals 1/2 times that mass times V squared, and solve for V. That'll tell you the velocity with which that electron strikes that plate, that positive plate. And 32, like I said, is just the opposite. You start with the velocity and work this problem backwards. But use the mass of the proton, because in problem 32 they're talking about a proton instead of an electron. So it's the exact same problem, but in reverse.